Okay, so hi guys. This is topic 1, lesson 2C. So this should be the last podcast for topic 1, lesson 2. It's going to be on phase change diagrams. And this morning, or today, I believe you did one part of a phase change diagram. You were doing a cooling in terms of a phase change diagram, a cooling diagram, because we took the diodonic acid or the lauric acid and we went from a liquid and went to a solid, and you took the temperatures every 30 seconds. And so what my hope is, in you collecting that data today and collecting some heating curve, taking it from a solid now to a liquid tomorrow and getting the data, that what you find out when you graph that data is going to be what I'll be talking about on this podcast and will be reinforced by this podcast. So that is what our hope is. So let's see if that actually occurs. So what is a phase change diagram? A phase change diagram shows the relationship between temperature and phase changes over a period of time, whether it being heated or cooled. Again, today what you guys did was you guys actually did the cooling aspect of it, but you will be doing tomorrow the heating aspect of it. So you hopefully did one section of this cooling curve today. Hopefully a part of this looks like what you did today in terms of the data, and then tomorrow some part of this is what you'll be hopefully getting as well. The cooling curve diagram usually shows up a lot better in terms of the data. The heating curve sometimes looks a little bit not like it's supposed to if you don't heat it evenly and slowly. So hopefully tomorrow you will be heating it evenly and slowly, and you'll get some great data. But nevertheless, let's go ahead and start to talk about what these heating and cooling curves actually mean in terms of energy. So here is a heating curve diagram, and what you're looking at is you're looking at it starting at a solid or something that's very organized. So we're going to start here as a solid, and then we're going to end up somewhere where it's extremely disorganized, which we understand that that's going to be a gas. So eventually we're going to end up with a gas over here. And this is as we are heating it. Now please understand, as time goes on, it's heating at a constant rate. It's at a constant, it's gaining heat energy from a constant source. So let's just say, for all intents and purposes, that for every 1 second, it's going to equal gaining 10 calories of energy. Okay, that's the CAL. I know that looks really horrible, but that's 10 calories. So as we go through here, every second, I'm putting 10 calories of energy or heat energy into this substance, whatever the substance may be. And as I'm doing that, in the beginning, that energy is being used to, as you can see on the y-axis, it's changing the temperature. So the temperature is increasing over time here. But then all of a sudden you get to B and the temperature stays the same. So we need to be thinking about why would that happen and what's going on in terms of phase changes at this point. So let's remember, when something is a solid, it still is vibrating in its movement. It's moving slowly, but it's vibrating. The cooler the temperature is, the slower it's vibrating, or its kinetic energy of motion. So as I'm adding heat energy to this, my temperature is rising, which again, remember, temperature is the same as kinetic energy. So I'm increasing kinetic energy. I'm moving faster and faster and faster and faster and faster. And eventually I get to point B, where all those molecules are moving so fast and vibrating so fast next to each other that they now can't even stay next to each other because they are moving so fast that they're able to escape each other's grip, I guess you would say. And as they escape each other's grip, that's what's happening from B to C. From B to C, one molecule is going away, and then another one, and then another one, and then another one, and it's escaping and getting a little bit further and further away. And now when we're a solid and we're able to get a little bit further and further away, we know we are turning into a liquid. So from B to C is actually when I am changing from a solid to a liquid. So this is extremely important, guys. When on a heating curve or even a cooling curve, when there's something flat, when there's a flat area, a plateau, that's when you are changing phase. And please write that down. When it is flat, that is when you are changing phase. Write that down. We are not changing temperature. We're changing phase. Now remember, temperature is kinetic energy. So we're not increasing our kinetic energy in any way, shape, or form from B to C. All the molecules are moving at the same rate from B to C. They are just taking that energy, because we're continually adding energy here as we go on. We're still adding energy. So why is that energy not making them move faster? Because that energy is being used up so that they can change phase. They finally got enough when they got to B that they could use it up. They put it in their savings. They saved up. Now they're using it to change their phase. And as they're using it, they're not gaining any more in their savings. Okay? So this, when it's on a slant, is when it's in one phase only. When it's at a plateau, that is when it is changing phase. So guess what this slant is? It has a slope. When it has a slope, it's in a phase, and that's going to be when it's a liquid. And again, now that every single molecule here has changed from B to C, has gone back and has changed, now, get rid of all that stuff. From B to C, it's all changed from a solid to a liquid. Now these molecules are moving faster, hence they have a higher kinetic energy at a higher point. And they're moving faster and faster and faster, and now they're sliding past each other and going all over the place. And as soon as they are running around so fast, or sliding past each other so fast, it's kind of like being ice skating, and you're like holding on to each other, but you're sliding past each other when you're whipping around. As soon as you go so fast, kinetic energy is increasing, that you get to D, then what happens is that one of those molecules has enough energy to pop away and become a gas. And now, again, where you're flat, this flat part is when you're going from a liquid to a gas. Remember, a zero slope means that you are changing phase. And you'll continue to add energy until you get to E. And that energy is being used now to increase the kinetic energy, because it's not increasing temperature, but it's being used to increase actually your potential energy, and therefore be able to change phase. And then from E to F, you're on a slant, so you are a gas from E to F. So let's go back and make sure I recap this real quick. So from A to B, it's on a slant, so it's in a phase, or it's in a phase, so this is a solid. B to C, it's at a plateau, so it's changing phase, it's going from solid to liquid. C to D is a liquid. D to E, plateau, liquid to gas. And E to F is a gas. Okay, now let's just really quickly talk about potential energy and kinetic energy. Obviously, kinetic energy is temperature, so from A to B, kinetic energy is increasing from A to B, C to D, and E to F. Potential energy is increasing from B to C and D to E. Okay? So potential energy is when it's flat, kinetic energy when it's on slant. So from A to B, kinetic energy is increasing, potential energy is staying the same. From B to C, potential energy is increasing, kinetic energy is staying the same. One other thing to note. If you look at this, you can see that B to C and D to E, these phase changes, have different times. So let's go back up to this one, every 1 second is adding 10 calories of energy to this substance. So it looks like it takes a lot, maybe 2 seconds to go from solid to a liquid, whereas over here it may take 4 seconds. So if I do that, this 2 times 10 is going to give me 20 calories. 4 times 10 is going to give me 40 calories. So it's going to take more calories to go from a liquid to a gas than it does to go from a solid to a liquid. And you need to know what those energies are called. So the energy that it takes to go from a solid to a liquid is called the heat of fusion. So the energy it takes to go from a solid to a liquid is the heat of fusion. How much heat does it take to do fusion? And fusion is for going from a solid to a liquid. You need to know that. You also need to know what it's called when going from a liquid to a gas. This one's going to make a little more sense. This is called heat of vaporization, because you're making a vapor, right? I don't know if you can see that last part, but heat of vaporization. So the heat of vaporization is more than the heat of fusion, and therefore it takes more energy to go from a liquid to a gas than it does to go from a solid to a liquid. So that is technically a heating curve diagram. Now, you tomorrow will be going from a solid to a liquid, so hopefully you will be reproducing this part right here, where you are going to increase temperature until it starts to liquefy a little bit. Then when it starts to liquefy, you should flatten out, and then once it's all a liquid, you should start to heat up again. So here's a cooling curve diagram, and just real quickly, it's basically the opposite of a heating curve. So if you're starting at a high temperature, you will see, and for this, for instance, you're going to be starting at a high temperature, which means you're starting as a gas, then you're going to liquid, then you're going to go to a solid. And I always, always, always encourage you to label your diagrams. You know, on your tests, when you get them from me, you can write all over them. Please do so. Label them before you even look at the question. You see a heating or cooling curve diagram, label it right away, and then when you actually get to the question itself that it's asking, everything will be written right there in front of you. Okay, so mark up the test and start to diagram real quick before you even look at some of the questions. So this is going to be going from a gas to a liquid, and this is going from a liquid to a solid. And so this is going to be gas to liquid is condensation, liquid to solid is freezing. Okay, so here we go. Same thing, you can see the times down here. It took from 2 to 4 to go from a gas to a liquid, or sorry, 2 to 6, which means 4 minutes. And over here, it went from 11 to 14, so it only took 3 minutes. So it did not take as much energy release to go from a gas to a liquid as it does from a liquid to a solid. And hey, that's another review here. This is an energy release, how much energy is released, and so this is exothermic. We go back to this heating curve diagram. Remember, this one we were absorbing energy, so this one is endothermic. So that's another, just a review here, that a heating curve diagram is endothermic because we're absorbing energy, and a cooling curve diagram is exothermic because we are expelling energy or releasing energy. Just a couple more points I want to make here. Liquid to solid is freezing, so what is the freezing point of this substance? Looks like to me it's 90 degrees Celsius. And then liquid, gas to liquid, that is the condensation. So what is the condensing point? 150 degrees Celsius. But that also, this is the kicker, if I go backwards and I make this into a heating diagram, I'd be reading from this way back. and it's going to be the same. Remember that boiling point and freezing point are intensive properties. Well, the freezing point, going backward from a solid to a liquid, that's melting. The melting and the freezing point are the same temperature. The condensing and going backwards from liquid to a gas, evaporation or boiling, which aren't the same things, but for all intents and purposes right now in your chemistry career it is. So the evaporation point or the boiling point here is going to be 150 also. So these points, when it's condensing, is also the boiling or the vaporizing. When it's going from a liquid to a solid or freezing is the same as when temperature is when it's going from a solid to a liquid, which is melting. Very important point. Melting and freezing point, same temperature. Boiling and evaporating point and condensing point, same temperature. So with that being said, if this temperature right here, if this temperature was 100 degrees, well, let's not say 100 degrees. If this temperature, hold on, let me take that out. If this temperature was 0 degrees, I know that this substance is probably water because this is the melting point, and which would also mean the freezing point. And I know water's melting point and freezing point is 100, which means that D to E, this would be 100 degrees Celsius because that's the boiling point or also the condensing point. If I look at if I look at the cooling curve that we have, this cannot be water. How do I know it's not water? Because right here is the freezing point, and that says it's 90 degrees Celsius, and water does not freeze at 90 degrees Celsius. So, again, intensive properties of boiling point and condensing point. So, yesterday's lab that you did do cooling. You went from a liquid, which would be here, to a solid, which would be here. So we are hoping that your diagram or your graph is going to look something like this. So now when you take your data from your heating curve and you take your data from your cooling curve of the lauric acid, you're going to do that both on the same graph paper, and since your melting point and your freezing point are supposed to be the same points for temperature, I hope you plateaued at the same temperatures. And I hope when you put both of those diagrams on your same graph, they're going to overlap. Now their time's not going to overlap because the heat of fusion is not going to be the same. This going from a solid to a liquid is not going to maybe take the same amount as going from a liquid to a solid in this case, depending upon how you heated the substance. Your time might not be the same, and you might not be using the same test tube of lauric acid, so you might have the same amount of it. But hopefully the temperatures will overlap, and I will see that soon when you turn that lab in. I'll see you tomorrow, and if you have any questions, please again write them down right away before you forget, and we'll go over them tomorrow.